How does the Schrödinger equation explain quantum mechanics? Imagine trying to predict the behavior of tiny particles like electrons and atoms. It's not like tracking a ball rolling down a hill. Instead, it's about understanding probabilities and waves. The Schrödinger equation is the key to this puzzle. It was created in 1926 by Erwin Schrödinger, building on Louis de Broglie's idea that particles can behave like waves. This equation is the foundation of quantum mechanics, which studies matter and energy at the smallest scales. It looks complicated, but at its core, it describes how the wave function of a particle changes over time. The wave function is a mathematical expression that contains all the information about a particle state. When you square its magnitude, you get the probability of finding that particle in a specific place or energy level. Think of it as a cloud that shows where the particle might be. The equation itself is a partial differential equation, meaning it relates how the wave function changes with time and space. It includes terms for kinetic energy, which depends on how fast the particle is moving, and potential energy, which depends on the forces acting on it. The potential energy can come from electric fields, magnetic fields, or other influences. When you solve the Schrödinger equation for a specific situation, you get the wave function that describes the system. This helps scientists predict phenomena like atomic stability and electron arrangements in atoms. It also explains why electrons occupy certain energy levels, known as discrete energy states. These energy levels match what experiments show, like the lines in a spectrum. The equation also accounts for wave-like behaviors such as interference and diffraction, which are key features of particles at tiny scales. It's important to note that the Schrödinger equation applies to systems where relativistic effects are not significant. For faster particles or very high energies, scientists use more advanced equations. But for most atoms and molecules, this equation is the main tool. Its development marked a major milestone in science because it shifted our view of matter from classical particles to wave-like entities governed by probabilities. This understanding led to many technological advances, including semiconductors, lasers, and even quantum computers. The Schrödinger equation shows us that at the microscopic level, matter and energy behave in ways that are fundamentally different from our everyday experience, opening a new chapter in how we understand the universe.